I think we are almost live on YouTube, but then what happens is it starts playing me back 30 seconds before myself, which is like freaky. So yeah, I think we are, there we go, we've got rid of that. So that is good. Okay, yes, good. We've got recording, we've got YouTube, we've got a plan, we're all good. We're up to 74, 77, more. Yep, this is recorded and it will be on there tomorrow morning, hopefully, on the same link that you clicked on to get to this, okay? But I want lots and lots of people. I want some more people, okay? Yeah. So anybody you know doing maths, you must know more people. We must be able to get to at least 300, I reckon, 300 people. This is so important. And also, like, I'm going to be marking your papers. So I want you to get all these questions right. And then I can go tick, 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 tick. And then it's all easy. Right. Okay. So your job, I'm assistant principal examiner. I'm not just examiner. I'm at the top. Okay. Go get more people, please. 86. I want like 500,000 people in my webinar. I want more than biology is the point. Thank you, Nima. Good one. Yeah, text them the thing. Right, let's start and then they can join in, okay? Right, first thing, we want lots and lots of people because I want lots and lots of people to do integration because it's so important. Second thing, I want you all to be able to integrate by the end. So make sure that you are asking questions and telling me how you're feeling about it, because I can slow down, speed up, change direction, whatever you want. Okay, I want lots of sign-ups to my course. I'm going to show you my course. I'm really proud of it. And there's a deal on at the moment. I don't need to slow down. I'm not even doing maths yet. There's a deal on at the moment where you get a third off, okay? And that makes it 60 quid. And it is really good. And I am proper proud of it. And I honestly think it's going to help you with your C3, C4. So I'm going to try and convince loads of you to sign up because then I can help you over the next 4 weeks. This is really important, not just how to integrate, but where people go wrong when they integrate, because otherwise you're just going to go la, integrate, and then, thank you. Yeah, I really like these. They like go through and then they go through the circle, like in one big thing. Thanks. And yeah, I haven't got a bouncer. So if anyone starts spamming the chat, really my only option, because I won't have time to go and find their email and chuck them out, really my only option is to click on this thing and basically turn the chat off, which is really not good because I want you to be able to communicate with me, okay? Right, so what I'm going to do is I'm going to go straight in with the integration, and then after about half an hour or so we'll stop and I'll go through the competitions that are on and remind you of where everything is, and then we'll carry on with integration. I definitely want to get as far as integration, parametric integration and differential equations by the end. Okay, right, can you see these 10 things? Good. Right, these 10 things, I'm going to say them out loud, so grab a pen and write them down. There is no such thing as integration, okay? There is no such thing. Okay, you're not integrating. What you are doing is working out what got differentiated, right? And there are only 10 things that could have been differentiated. There are only 10, and they are these 10, okay? So first of all, what we're going to do, I'm going to leave these here, but grab a piece of paper. I'm going to say them out loud and I want you to write them down, because literally there are only 10 things that could possibly have been differentiated, and integration is working out what got differentiated. So all of integration is literally choosing one of these 10. That is it. Okay, I'm going to say them out loud. I didn't want to write them on here because I wanted the board for writing on, obviously. So we have got sine. Okay, I'll write them here, but then I'll rub them off. So we've got sine, cos, sec squared, cosec squared, sec tan, cosec cot. Okay, there's 6 of them. Sine, cos, sec squared, cosec squared, sec tan, and cosec cot. There's 6. Then the other 4 is e to the a to the, a is just a number that isn't e, and then brackets to the power of -1. Let's move tan over a bit. And brackets to the power of n. Okay? You all still there? Chat's gone on. Cool. Right. Everything we do is going to come back to these 10. Okay? Everything we do. Sine, cos, sec squared, cosec squared, sec tan, a is just any number, cosec cot, e to the power of, a to the power of, like 3 to the power of, or 2 to the power of, or 7 to the power of, stuff to the power of -1, and stuff to the power of n. Okay? And what these 10, they're not just out of thin air, they're the things that you differentiate. Okay? We're on 104. We need to double, triple our count here. Okay? Who's got a friend? One that does maths, not one that doesn't do maths. No, these are the only things that can be differentiated. And what you're doing with integration is you're working out what got differentiated. So, well, does anybody know another function that you could differentiate? I'm a bit blurry. I don't know what to do about that. Oh yeah, duh, yeah. But this one has come from learn, yeah. This one, that one's come from learn. So that includes learn. I don't know how to make me not blurry. Sorry, because I don't know. You might just have to put up with blurry me. Tan differentiates to sec squared. Got that one. Okay, so these are the derivatives. These aren't the things you differentiate. These are the derivatives. So this is what you get when you differentiate cos. This is what you get when you differentiate sine. That's what you get when you differentiate tan. I don't know if you can turn chat on the bottom of mine. If I click on chat, then it kind of disappears. And my lights are not turned off, but the trouble is if I put any more lights on, they reflect off this screen and then you can't see the screen. You can't see this properly. Yeah. Minus we can deal with. Don't worry about that. Don't worry about minuses. Okay, just don't worry about it. Yeah, we can deal with minuses and numbers and stuff. Okay, so if I differentiate cos, I get sine. If I differentiate sine, I get cos. If I differentiate tan, I get sec squared. If I differentiate cot, I get cosec squared. I know I'm not doing the minuses right. I don't care. That I'll deal with that later. If I differentiate sec, I get sec tan. My screen brightness isn't going to make any difference to, is it? Does that make a difference? No, that's what I thought. Because it's the camera, isn't it? No. Can you see that is the point? Beautiful as I am, this is the most important thing, okay? That's what you need to see. Good, good. Right, these are the only things that we are going to integrate, because what integration is working out what got differentiated. And if I differentiated something, I must have ended up with one of these, because we only know 10 things that we can differentiate. Sine, cos, tan, sec, cosec, cot, e to the power of, a to the power of, ln, and x to the n that you do in the first year. That's it. Okay? Yeah, but a function is made up of those 10, isn't it? It's a product of the 10, or a quotient of the 10, or a chain, like with something in something. That's the only functions you know. Sine, cos, tan, sec, cosec, cot, e to the, a to the, ln, and x to the n. You don't know any other functions. All the functions that you deal with are combinations of those 10 functions, either put together in a product, put together in a quotient, or put together in a chain, in a composition. No, you don't know any other. What other functions do you know? There aren't. Oh, I see what you mean. Are they given in the formula book? They give you the derivative in Edexcel. They give you the derivative of tan, sec, cosec, and cot, I think, but that's all. Okay, so let's quickly look at the derivatives, because that's the whole point. The whole point of an integral is that I write down this, okay, and then I put a thing here, and in my head, I differentiated something, and I've written it here. So for example, maybe I differentiated cos 2x, like that, okay? In which case, when I differentiate cos 2x, I get minus 2 sine 2x using the chain rule, okay? So then I give you a puzzle. Maybe I make it a little bit hard by getting rid of this. And maybe I just say to you, right. So I'm not giving you the minus 2, I've just given you that bit. And then I'm saying, what did I differentiate? That's what that says. What did I differentiate that's ended up with sine 2x? Okay, exactly. So what you do is you look at this thing here and you say, right, well, I've got a vague idea of what you differentiated. You must have differentiated. Well, this is sine, right? Sine has come from cos. So you must have differentiated cos. It's not, you can't differentiate like x cubed and get sine 2x, can you? You must have differentiated cos. So we can write down immediately cos 2x. Now that might not be the end of the story, but it's at the beginning of the story at least. Then you differentiate this and you think, is that right? Did it? No. And then you think, right, well, if you differentiate cos, you get minus, so I'll put a minus there and the minus can cancel. And then so what happens if I differentiate that? Does it equal that? No. Almost, but no, because of the chain rule. So the chain rule would force me to multiply by 2, because I would get sine 2x, and then I'd have to multiply by the derivative of this, which is a 2, and then there would be a 2 there, and I don't want a 2 there. But it's really easy to deal with that. You just put a half there. That's all. And now, if you differentiate this, the derivative of cos is minus sine. The minus cancels. That's why I put it there. Then we get sine 2x, which is, that's working, that's good. Then we use the chain rule and we multiply by 2, but I put a half there. So the 2 times the, well, you do divide by the derivative of the brackets, but that's not how I would think about it. I would think that I want to put something there so that when the 2 comes out, it cancels, okay? So explaining again, I look at this and I think, what did you differentiate? What did you differentiate? I know you differentiated cos. So I write down cos and I leave that angle the same. I write down that immediately. That's what my first thing looks like that I write down as my sort of guess. Then I think, does that work? If I differentiate cos 2x, do I get sine 2x? No, because the derivative of cos is actually minus sine. So if I put a minus there, then the minus that I get from differentiating and this minus will cancel. And there's a chain rule 2 coming out. So I'm thinking through what the derivative is, and I'm putting compensation in place here, okay? Now there are only 10 things. There are only 10 things. So all of integration is going to come back to these 10. So I'm going to make sure you know what the 10 are, okay? So what things do we differentiate? Sine, cos, tan, cot, sec, cosec, e, a to the minus 1 and to the n. Yeah, Hannah, that is true, but just bear with me and just see if you can see that this makes sense just in general. Okay, these are the only things we differentiate. So if I give you an integral, this is the answer, is one of these 10, 100% is one of these 10. So we need to know what these 10 differentiate to. So the derivative of sine, that goes to cos. All of these ones at the bottom, these ones that start with C, they go minus. So C, C, C. Anything that starts with a C, the derivative is negative. Anything that doesn't start with a C, the derivative is positive, okay? Right, there's another thing that you can do to remember. So the derivative of sine is cos, and the derivative of cos is minus sine. That's pretty easy, everybody knows that one, don't they? Right, these two are the two that have squareds, okay? And these two are the ones that have two terms, but The first, what's quite nice about laying it out this way is that the first word that you write here is the first word that you write here, and the first word that you write here is the first word that you write here. So tan goes to sec times sec. Sec goes to sec times something different. Cot goes to cosec times cosec, which is this word here, by the way. Cosec goes to cosec times something different. Okay, so sine goes to cos goes to minus sine, tan goes to sec times sec, cot goes to cosec times cosec with a minus. This is differentiating. Sec, look, the word that's missing is tan. Cosec, the word that's missing is cot. Okay, so tan goes to sec sec, sec goes to sec tan, cosec, cot differentiates to minus cosec squared, cosec differentiates to minus cosec cot. And the word cot is there and the word tan is there. So it's a really nice way of like putting it out. CD music system, cos differentiates to minus sine. Cos differentiates to minus sine, CD music system. SIM card, sine integrates. Yeah, see, but this is the whole point, right? I'm going to go faster in a minute because I want to move past these 10. But I think that it's very confusing for the brain to try to differentiate as an active process and also integrate as an active process. I think it is much, much, much easier and cognitively less demanding to only have as an active process differentiation. So there is no, exactly, because they're too similar and backwards. So if you don't, basically, you don't have to ever integrate. If you just differentiate, then when you see an integral, then you're just writing down what was differentiated, okay? So you're only ever differentiating, you're never ever integrating, there's no such thing. As soon as students try to integrate, that's where it's go wrong. Right, so these 10, e to the, obviously just goes to e, a to the x differentiates to a to the x ln a. Something to the power of n, the n comes down and changes, and something to the minus 1 differentiates to, oh, sorry, ln, that was the wrong way around. Ln differentiates to 1 over. Okay, now these are all derivatives, not integrals, but that's the whole point, is because we're not actually going to integrate anything. Right. Ready? I'm going to try some now. Right. What did I differentiate? What did I differentiate? I started with an easy one. So don't try to integrate. Do not try to integrate. Stop trying to integrate. Okay? If you try to integrate, then you're liable to start making slips. Okay? Instead, force yourself to think, what got perfect? What got differentiated? Exactly. So you're always differentiating. So what got differentiated? That, does it work? Not quite. We need a quarter and then we need plus c done. Okay? That's how you do it. Right. Nearly every single integral that you get fits into one of these 10. Okay? Yeah, they did all forget plus c. So what about this one? What did I differentiate? I didn't differentiate sine. If I differentiated sine, I would have got cos. If I differentiated tan, I would have got sec squared. If I differentiated ln sine, I would have, yes. What did, don't try to integrate. This is my biggest bit of advice to you, okay? Do not try to integrate. Stop trying to integrate. You're integrating. Stop it. Think about what you're saying. You're saying that I differentiated sec squared. What would happen if I differentiated sec squared? The 2 would come down and change to a 1. Then I'd multiply by the derivative of sec, which is sec tan. Right? That's not what I differentiated. Angeline, the point is, Do not try to integrate this. Think about these 10 things, right? There are only 10 things that I could possibly have differentiated. I could have differentiated sine, cos, tan, sec, cosec, cot, e, ln, exactly. You have to know how to differentiate. That's the point. Ln, I differentiated ln. Yeah, you just work out what was differentiated. If you try to integrate, that's when you get confused. So in this case here, you think to yourself, what was it that I differentiated? Now, if I differentiate ln of something, what do I get? If I differentiate ln of something, I get 1 over, exactly, right? I get 1 over that thing there, 1 over something. So if I differentiate ln of something, I get 1 over the something. And then what does the chain rule tell me to do? Chain rule tells me I now have to multiply by the derivative of this thing, right? Exactly. So this isn't the end of the story. I now need to multiply by the derivative. So when I multiply by the derivative, usually I just put it on the top. Now, do you agree with that? Right? So if I give you an integral and you see that it's a fraction and you see that the derivative of the bottom is on the top, then you know that what I differentiated was ln. Do you agree with that? Right, so this one here, what I differentiated was ln sine x. Exactly. Okay? Right, let's try another one. And I'm just going to bash on for another like 10 minutes with these ones because nearly everything is these ones. Okay? What about then... hang on, I need to do maths. Hang on. Plus, hang on, 8. There. What did I differentiate? Ln, good, ln. I differentiated ln. How do we know? Because it's a fraction and the derivative of the bottom is at the top. Almost. I mean, we're going to have to do a bit of fiddling with numbers, but it's not a big deal to do fiddling with numbers. It's ln. I differentiated ln. That's why I differentiated, because I got 1 over. Then I multiplied by the derivative of this, which is 8x plus 2. Yeah, exactly, we needed 2, because this doesn't say 8x plus 2, it says 16x plus 4. So this isn't quite right, we needed 2. But that's it. Okay? Don't worry about when to factorise for now. Yeah, but Eleanor, the reason you think it was a half is because you're trying to integrate. That is why. Don't try to integrate. It's too confusing. It's too confusing. The whole point is all of integration is inspection. All of it. Yes, I will do substitution once you can actually integrate, because all that substitution does is turn it into one of these 10. That's all substitution does. What does parts do? Turn it into one of these 10. What does partial fractions do? Turn it into one of these 10. Everything. Trig equations, they turn them into these 10. All you're doing with the whole of integration is bringing it back to this situation where you know what got integrated. That's all. So you're looking at it, sorry, not what got integrated, what got differentiated. You're looking at it and you're saying, what was it that got differentiated? Okay. The whole of integration comes back to that. Yeah, the whole of integration is working out what got differentiated. Right, let's try something like right. No, see? No, not parts, no. Too complicated, overcomplicating it. What got differentiated? E, exactly. E. E, exactly, right. So what got differentiated? E. If you can differentiate, you see, then you can do this because you can work out what got, it's like a little puzzle, what got differentiated. So what happens if I differentiate e to the x squared plus 1? I get e to the x squared plus 1, but then I have to multiply using the chain rule. Then I have to multiply by the derivative of this, which is 2x. Now that almost says 2x, it says 4x. If I put a 2 at the beginning, then that 2 and the 2 from there can combine, and then it'll be a 4x, and then that's the end. Okay. Right. Literally, this is what integration is, okay? This is the whole thing. Right. Do you want to try a slightly harder one? But it's the same thing. It's the same thing. 2 I got because I'm not integrating, I'm differentiating. I'm writing this down and I'm thinking, what do I get if I differentiate that? Right? What do I get if I differentiate that? I would get e to the x squared plus 1. Good. But then I'm not going to divide. No, I'm not going to, what I'm going to do is put the thing that I need there. That's what I'm going to do. I'm going to put the thing I need in. So if I differentiate this at the moment, I would get 2x. I would get 2x e to the x squared plus 1. That's what I would get. And I want 4x. How exactly, I mean, I'm not going to do this, but how exactly do you think you would do parts here? That would be your u, would it? That would be your, oh, right. In which case, okay, I'm going to try and not be sarcastic. In which case, if that is your u, how are you going to integrate? Because you differentiate u and integrate dv, right? So if you're doing parts, how is it exactly that you're going to integrate that? No, you can't, can you? That's the whole point. It would make it much worse. It'd be much worse. This is the thing. You write an integral in the exam, you put two things together, students do parts, bang, they're doing parts immediately. Look at this one. How to get students to do integration by parts. Yeah, you're right, Nathaniel, I actually can't. How to get students to do parts, you could do something like this. Right. No, no, see, don't. No, this is the thing. You're making integration so much harder than it is. You're overcomplicating it. There is only one method, Angeline. The only method is that the thing you're looking at is one of these 10, and then you write down what got integrated. And I'm going to, in a minute, say, right, how do you turn some other things into those 10? But if you don't recognize those 10, then what is the point in integration by parts or substitution or using partial fractions or anything? What's the point? Because what they do is they bring you back to these 10. But if you don't recognize when you got one of these 10, then what's the point? What's the point? The 10 things are the only things that could possibly have been differentiated. Sine, cos, tan, sec, cosec, cot, e, ln, a, x to the n. What you would do is you would say to yourself, so you see an integral, right? And you say to yourself, almost certainly, this integral is just something that got differentiated using the chain rule. That's probably what it is, right? So I'm not going to leap ahead and try and do some complicated stuff. I'm going to really think it through. Yeah, the flow chart, I'm going to give you a flow chart, but essentially this is the bulk of it. This is the big thing, right? Now, have a look at what we have here. We have got some stuff to the power of 4. Agreed? Right. Now, what happens if I differentiate that stuff? The thing that's here is the derivative of that. Yeah? You don't need to show working out. There is no working out. There is just looking at it. That's it. You'll get a method mark for the shape or the structure and then an accuracy mark for the detail. Okay, but what you see when you look at this, what you should see is that differentiated is this. So you see the chain rule, you see that the chain rule has been used. You're thinking to yourself, what got differentiated? I'm not saying you never have to use parts. I'm saying the majority of the time that you have two things times together, it is not a parts question. Sometimes they say using integration by substitution. I don't think I've ever seen them say using integration by parts, but they could. Yeah. Yeah, if it says use integration by parts, use integration by parts. But I don't remember seeing an instruction like that. Okay, so you have an integral. What you're looking for is that somebody has differentiated something using the chain rule. So here, that is only there because they used the chain rule on this, the person that was differentiating. So what did they differentiate it? They must have differentiated that. That must be what they differentiated. No, we're on 120. It's rubbish. Biology gets like 450. Don't understand. Yeah, it is. Yeah. Yeah, Matt. See, I don't get it. Anyway, let's get this sorted. Right. So the main thing here is the way that you think about integration. Okay. The way you think about integration should be what got differentiated, not how do I integrate? Because if you think how do I integrate, then you're thinking of this as an active process, and then you can get really, really muddled. So for example, here you'd be expanding out or using parts or da-da-da-da-da, okay? If you think of it as what got differentiated, then as soon as you spot the derivative of something somewhere else, you can see that the person just did the chain rule. So you can see what they integrated. So this person, sorry, differentiated what they differentiated. This person differentiated this. That's what they differentiated, okay? So let's think this through. They would have pulled the 5 down and change it to a 4. So if I stick a 5th here, then when that 5 comes down, it'll have a 5th to land on. And then it will change to a 4. And that's why that's there. Then the chain rule says I need to multiply by the derivative of this, which is e to the x. There's the e to the x. That's the end. Okay. Yeah, I'm going to do a few more examples, but then we need to do some other stuff to see how you get back to this, okay? I've put lots and lots and lots of examples on my course. Lots. If it was e to the 2x outside the bracket, you would have to do it by parts, yeah, because the derivative of that isn't that. So yeah, yeah. The e to the x hasn't gone anywhere. When you differentiate this, you use the chain rule. So you get 5 comes down, changes to a 4, and then you multiply by the derivative of this, which is e to the x, which is there. It's not that they cancel, it's that I am not integrating. I am working out what got differentiated. The course is available. I'll show you in like 10 minutes where it all is. Okay, let's try one more like that looks similar to this. Let's try something like, okay, do you want hard or easy? Hard. All right, fine. Wait, I haven't finished. Wait, I haven't finished. All of these ones I'm doing now, you can just write down the answer, okay? None of these require any work, any thought, anything. You can just write down the answer. You can just look at it and know what I differentiated. I didn't differentiate sec, I would have got sectan. I wouldn't have got sec to the 4 tan. If I differentiated a 5th sec, right, you're not thinking. Oh, a quarter sec to the 4, let's try that one. 1/4 sec to the 4x. See, what you're trying to do is you're trying to integrate. So you're chucking down these answers like, is it this? Is it this? Is it this? What you should be doing is differentiating. Now you've got it. Now you've got it. Good. Right. The idea here is that this one is a little bit sneaky. And what would be better is if I write this. So this is a slightly sneaky one. Slightly sneaky, right? What is the derivative of sec? Sectan, yeah. The derivative of sec is sectan, right? There is the derivative. Can you see that somebody used the chain rule? When you use the chain rule, you multiply by the derivative of the thing inside. Somebody used the chain rule. So what was it that they differentiated? Sec to the what? What got differentiated? Exactly, sec to the 4. Exactly, sec to the 4. Right. So what got differentiated was sec to the 4. Do I need anything at the front? Exactly. Done. Okay. So I am not integrating. All I am doing is I am working out like a puzzle, like a fun game. I'm sure you don't think it's fun. Practice. You need to practice. Basically, this is, look, I'm going to do my sales pitch now. Okay. So how many of you are in here? 121. That's not that many, but so I've been teaching 15 years and not in private education, in state education. And 75% of my students have got B or A star. Okay, 75% over 15 years in state education, and 1 has failed. So that's 99.95% pass rate and 75% B, A star. Okay, I know how to help you, and we have 4 weeks. I mean, get a U. Like no one, and my students do not fail. Most of them get B or A star, right? I don't teach anymore because I'm doing this. So I've got the next 4 weeks, I am literally being paid to sit at a computer helping you. That is it. That is my job. So I've made this course, which I will show you, and I think it's going to be really helpful for you, but also I am available. The point is you can put comments on, you can put questions on, and I'm just going to, literally, I'm here all day just to help you for 4 weeks. If you want more videos, I can do more videos. If we, that is my job. My job is just to help you. And if you use this, 1/3 off thing, then it's 60 quid. It's 60 quid. I would charge that for an hour. You're going to get 4 weeks of me like on demand. It ends midnight. It ends midnight on Sunday. So let me just show you, and then we will go back to the integration and we'll do some substitution and stuff. Okay. If you paid in full, then do office@tailoredtutors.co.uk and just say you didn't know about the 1/3 coupon, and I'm sure they'll help you with that. Right. So let me just show you what I have made. Share screen, and then we'll go back to the integration. But I do think this is important because like really, I can really help you over the next 4. You can go up a couple of grades. We can fix it. 4 weeks is such a long time. So here's the Tailored Tutors website. Can you see that? I can't see chat, so I don't know if you can see it or not. And if you go on packages and pricing, then you see the 3 things. And if you want to see what is in there, then you click on view kit contents, and then that's going to show you what's in there. So for example, if you go in the calculus, then what you're going to get is, so say you want integration, right? We're doing integration today. So go down to integration, right? So you get a video going through that backwards chain rule method, working out how to integrate. You get another video, which is loads of examples of backwards integrating, like working out what got integrated, the thing I'm doing here. loads and loads of that. Then you get a video about integrating trig, a video about integrating fractions, parts, substitution. Then you get a whole load of practice just of that with video solutions. Then you get some trig and some parts, just a few questions to see whether you're any good. Then you get all of the past papers from the last 5 years, all the past paper questions with solutions. And then you get a whole bunch more, a whole pack of all the past paper questions that I could find on AQA, OCR, EdXL for the last God knows how long, with video solutions, and then trig and then parts, right? Plus, all of those you can put comments on and ask me questions, all of them. So you can, if you're stuck in any way, you can just put a comment saying, at 3 minutes you said this, what are you talking about? And then I will reply to you, okay? And then you've got it for areas under curves, parametrics, differential equations, volumes of revolution, everything that's in C3, C4. The one that I'm really pleased with is this one. This is guided past papers. Is just if you do a whole paper, you can just click on this and like go through C3 2015 or whatever. This one is going to be really good. This is for when you don't know what revision to do. So you go to the day that it is. So it's going to start on Monday the 21st, and you will get 2 questions. So if you haven't got much time or you don't know what to do, you're not really in the mood, you can just go to whatever day. It's like a lucky dip of what might come up in your exam. So say it's Friday and you go, right, I'm going to have a look at this and I'm just going to do a couple of questions, and you click on that one. You get 2 questions. One of them looks like that. And I've chosen them because they're a good reflection of what could be in C3, C4. So that's that one. And then the next one, which I need to upload, I'll do it tomorrow, is one where I've done the answers, but I've made classic mistakes, like the mistakes I see in the exam all the time, the mistakes that I know students will make this year in the exam. So you'll get 2 questions, and you can just log on. You can have a look at other days as well if you want, but lucky dip, if you go to that one, maybe this is the one that's going to be in your exam. And then the next day, so this is Friday, the next day, the solutions will be put up Saturday. And I'm deliberately holding off slightly on the solutions because I want you to have some time with the question where you don't have the solution, so that you don't have that temptation to just look at it. Okay, so there's all of that stuff. There is also the web class series that you can click on. You can, what else is there? Free resources, the exam training week is what we're in at the moment. And if you use the code 1/3 when you go to buy it, then you get a third off, which makes it, instead of 90 quid, 60 quid. So I know 60 quid is not no money, but if you can, we've paid 30 quid in, basically. You pay 30 quid in, get your parents to pay 30 quid in, or say to them, can I do something for you for 30 quid? And then can I buy it? Because it's going to really help. Because it isn't just a whole load of videos. That's the whole point. It is me on demand for 4 weeks is what it is. So that is my sales pitch. Oh, is anyone doing, remind me D1, I've got a link to some D1 videos that I was going to show you. And yeah, I think that's YouTube. So that is all, that's what's in the course. And I will try to come back to this now, stop screen. Okay. S1 and S2 is, I'm going to do webinars on them. So I haven't made videos on them, but I'm going to do webinars on them. Okay. Yeah, you've got 4 weeks, you've got loads of time, but this is the other thing. You can message me or email me. Like if you're on that paid course and you've got it, 60 quid, then you can send me messages saying, what about this, what about this? And then I'll reply to you. You've got me in your pocket. Okay. Yeah, you can go from a D to a B. Yeah, up to. I would expect up to. For if I was working with someone from now, I would expect up to. Why would, look, right, we're working proper hard and we've brought the price down as low as we possibly can. And I really, really think 60 quid for the amount of time you're going to get from me and from the others, I really think is worth it. So to share an account, I don't think you can log in at the same time anyway, but you know, we're going to give out free kits on Sunday at 6 o'clock. Sunday at 6 o'clock, we're going to say the winners. There's going to be Instagram winners and Facebook winners. So if you leave a public review on Facebook, of all the public reviews, I'll tell you what, remind me at the end and I'll just put a link to the D1, okay? Of all the public reviews on Facebook, we're going to pick one to be a winner, and that person will get the course of their choice for free. Of all the people that have followed us and tagged someone on Instagram, one of those will, and then there'll be one person per webinar as well that will be chosen to get it for free, and we'll reveal, do the Instagram then, and then we will reveal them on Sunday. M1, I'm doing 2 webinars on M1. 2 webinars on M1, 2 on S1, 1 on S2 or 2 on S2, the rest are on C3, C4. The course I think is really good. I'm putting up more and more all the time. I'm not doing FP2, FP3 at the moment, no, because there wasn't time. This video will be available, yeah, it's being recorded. Right, we need to do some more integration now, okay? So, what happens, the whole point of this, put this board back, the whole point of this is that if I give you an integral like, for example, this, okay, then you need to work out what I differentiated, and you can't because it's really not obvious what I differentiated. Exactly. So if you get fractions, 3 options for fractions. 1 is actually really easy and you're just being silly. So for example, that, okay? No need for partial fractions, no need for anything, no need for anything complicated. This is literally just u over root u, which is u to the half. This is just a first year one. Yeah, C1, C2, exactly, okay? Don't need anything. So fractions, maybe it's simple, maybe you can simplify it, right? If not, there's only 2 options. Well, I suppose we ought to remind ourselves what happens if I put on the top here. What got to be learn? Good, learn. Exactly. So the first thing you're thinking about with a fraction, you're going, what's the derivative of the bottom? What's the derivative of the bottom? The bottom is x squared plus 3x plus 2. What's the derivative of the bottom? 2x plus 3, it's on the top. So somebody's used the chain rule. So they must have just done that. That's what they differentiated. So they got 1 over x plus 1, x plus 2, and then they multiply by the derivative of that, which is 2x plus 3, and that's why that's on the top. So the first thought that you should have with a fraction is the derivative of the bottom on the top? Because if it is, it's ln. Okay, next question, can I simplify it really, really easily? So for example, something like x plus 2 all over x squared. Okay. Prove that the derivative of ln is 1 over x, no. So this one is just that, and that is no work, no work. I'm not doing parts, I'm not doing substitution, I'm not doing all these things that you think of as integration. Why wait? X squared. No, good point, good point, good point. Better? My 2 did disappear. Yeah, this is what happens. Numbers are evil. Good. Right, so this is what we have. This is you look at your integral, and the first thing you think, try not to move away from this. Try to think, yeah, that is what I'm doing, yeah. Try to think what was differentiated, okay? What was differentiated? And if you can see sine and then its derivative, that means somebody used the chain rule. If you can see cos and then that thing's derivative, somebody used the chain rule. If you can see sec squared and then its derivative, somebody used the chain rule on tan. If you can see sec tan, cosec cot, cosec squared, all of those things, if you can see the derivative of that thing, you just know that somebody got the chain rule. Somebody is the person who differentiated it. Right. So let's say then we have a fraction. The fraction might be easy, or you might need to use partial fractions, or you might need to use algebraic division. They're your only options. Or it's come from learn. Okay, that's it. That is the only options. For a fraction, either it's come from learn, because the derivative of the, so it looks like this. It's got something down there and it's got its derivative on the top. Then we know what got differentiated. It was just learn. Okay, the last one is algebraic division. So how would we know the difference between these two, for example? What would it look like if I was going to have to use partial fractions? Yeah, top heavy or bottom heavy is the big difference. So partial fractions is where the bottom is really heavy, and algebraic division is where the top is really heavy. So top heavy things might be like a cubic on the top and a quadratic or something linear on the bottom. That's top heavy, that's algebraic division. If you have a bottom heavy thing, then you have something like a quadratic on the bottom, or even a cubic maybe. And then you have something smaller on the top. So this is bottom heavy because the bottom is heavier. And then if I make that a 5, that's now top heavy. Yeah, you can do that. That's going to work out. That's a good little trick. The +1 and -1 in the numerator is a good little trick when they're top heavy. Do that if you want. I'm not going to go over that just because it produces the same effect as algebraic division. Okay. So you've got your integral. You're not panicking. You're thinking to yourself, all right, what got differentiated? What got differentiated? Can I see that somebody used the chain rule? Can I just write something down that got differentiated? Right, next, let's say it isn't that. Is it a fraction? Are you sure it's not that the derivative of the bottom is on the top? Because in which case it was just learn. Or maybe it's easy. Maybe it's just something from C1 that you can simplify. Okay, fine, let's say it isn't either of them, in which case you're either doing partial fractions for a bottom heavy thing that's probably already factorized, or algebraic division if it's top heavy. That is it. So that pathway of thought gets you to a decision about what you're going to do. Yes, there is a video on division, everything in C3, C4. Okay, right, trig. Almost all trig, don't forget, has come from something you can just write it down. If it isn't, then it's one of these ones, and these ones you're supposed to just know what to do. Okay. Sine squared x, you're meant to know what to do. Cos squared x, you're meant to know what to do. All the squareds, you're meant to know what to do. Okay, good. So sine squared, you change to a half 1 minus cos 2x. Cos squared, you change to a half 1 plus cos 2x. Tan squared, you change to sec squared minus 1. And cot squared, you change to cosec squared minus 1. Yeah, exactly. You can use the hexagon. Yeah, exactly, for these two. So these are just standard expected trig things that you're meant to be able to do. So you don't really, they're not the 10, but you are meant to know, you know, it should be fairly obvious. 1 minus cos 2x. Sine squared x is a half 1 minus cos, and then you double the angle. Yeah. That's not the chain rule. You would then use the chain rule to work out what got integrated, but this is just the double angle formula rearranged that gets you to something that then you can work out what got integrated, that's all. Everything comes back to turning it into something that you can see what got integrated. I keep saying that. What got differentiated? What got differentiated? Okay, so first thing is it just something that somebody differentiated using the chain rule? Second thing, if it's a fraction, think through these three options. And if it's trig, is it one of these 4? In which case, the hexagon thing is on YouTube from yesterday or the day before. You go and watch the thing that's on YouTube. It's from like a couple of days ago. Sine squared x, what you do is you just don't write sine squared x, you write this. That's how you do it. Instead of writing down sine squared, you write down that. And then you know what got differentiated, then you can just write it down. Yeah, but I want to move on to substitution and differential equations. Okay. Because also on the course, there are so many examples. I've done done hundreds of examples, because you get it when you've seen loads. Then you go, oh yeah, I see what's going on now. You can't really see it from 3 or 4 examples. Okay, so we've done things where somebody differentiated it using the chain rule. We've done fractions and we've done trig. That covers everything apart from substitution and parts. Everything. Literally, you would not be able to come up with an integral that isn't that, or them, unless it's substitution or parts. Okay, so now we'll move on to substitution and parts. Now, I'm going to go really, really fast on parts because I think it's easier than substitution. Parts, when do we do parts? There are 2 situations. Okay. Situation 1 is that you've got a thing here and another thing here, and that is what you are trying to integrate, and it's quite hard, okay? But if you differentiate that one, and integrate this one, then you get 2 things which is actually quite easy to integrate. So this is the question that you're given, and this is what you turn that question into, these 2. So you write down what U is, and there's a acronym for thinking about what U is. First of all, are there any logs? If there are any logs, they're U, like ln. Ln would be U. If not, is there any algebra, like x cubed, x squared, anything like that? Is there any trig? Is there any exponentials? So yeah, that's the order in which you would decide what U was. So first of all, if there's any logs, they get to be U. If there isn't any logs, then algebra gets to be U. Yeah, indices, logs, algebra, you can have an I here. Indices, logs, it doesn't really matter actually which way around they go, but algebra, like squared, cubed, to the 4, to the 5, blah, 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 trig, exponential. So that, what that tells you is which one gets to be U, all right? So this is what the question is asking you to integrate, and that's what you're actually going to integrate. Question, actual fact, right? Indices like the other way around, like 2 to the x, not x to the 2. I just think of it like that. Logs, algebra stuff, trig, exponentials. Okay. So the formula is these 2 minus the integral of these 2, uv minus v du by dx. Those 2 minus the integral of those 2, that's the formula. So you would, so let's do an example, and then we're going to move on to substitution because that's harder. So let's do 4x ln x dx. What's fuzzy? The board? Don't know how to focus it. Anyone know how to? Okay, cool. Maybe if I just write big so that you can see it. So 4x ln x. So we go u and dv by dx. That's what we're choosing. And have we got any logs? Yes, we have. So that is going to be what u is. And the other thing is going to be dv by dx. That's what they're asking us to integrate. But we're not going to integrate that. We're going to integrate these 2. That's what we're actually going to integrate. So to get down here, we differentiate. And to get up here, we integrate. All right so far? Okay. Now, the formula says that this integral, which is these two times together, is the same as those two times together, exponentials. Those two times together minus the integral of these two. And that's what we end up integrating, is the other diagonal. Okay, so the formula says that this is the same as these two times together, the top two. So 2x squared ln x minus the integral, and then this is what we actually have to integrate. But this is going to be so much easier than integrating that. That we've got no idea what somebody differentiated. Whereas this, look at this product here. This product, 2x squared times 1 over x is just 2x. Now it's obvious. It's obvious what somebody differentiated to get that. They differentiated x squared. It's really annoying that it's fuzzy because I have absolutely no idea how to focus it. Is it because it's trying to focus on me? Maybe if I move here. All right. Okay. The internet should be fine because I've paid for like the most expensive you can possibly get because I got so angry with it. So it's like Virgin, super duper, fiber optic, mega, everything you can. Oh, I see what you mean. Yeah. If my connection is weak, Virgin are getting a phone call. Yeah, I think it's that what it's trying to do is refocus on me. So I think I need to just stay still next to the board and not move. I think that's what I need to do. Right, so you get a product, you put the u here and the v dx here, integrate, differentiate, and then the formula is these two multiplied together, minus the integral of these two. So instead of integrating that, you integrate that. That will be easier. This that 2x is these two times together. So it's 2x squared multiplied by 1 over x is 2x. That's 2x there. Yeah. Yeah, the lighting is really hard. I did spend ages fiddling with it earlier because I have to get it like on the board but not reflecting off the board, which is difficult. But anyway, right, I am not spending ages on parts, okay, because it's just a formula and students tend to be a lot better at parts than at substitution, and I want to show you how easy substitution is, okay? Because sadly, we do not have the entire night, much as I would love to do integration with you all night. Right, let's do a substitution. Actually, a substitution I'm going to look at once I wrote down because I'm not going to make up a substitution because they tend to be more weird. Okay. Hi, Rich.
I'll unmute myself. Hello.
Hello. Can you all see Rich?
Maybe if I talk. I think if I talk, I'd take over and then they can see me and I can be quiet.
Do you want to keep this meeting, end meeting, new meeting, cancel? Where are you?
Oh, I'm just going to be quiet. I've got to plan my lesson on my web class coming up. So I'm going to sit here and just make sure everything's, that looks very fancy. What's going on there? I don't understand any of it.
Integration by substitution. They're excited for biology.
Are they? Well, yeah, I best get on and plan my lesson then. So it's, I am in London, in swanky East London, Shoreditch, in a fancy office with ridiculously high-speed internet.
Nice.
Yeah, I'm going to mute myself and disappear.
Just don't even talk about it at the count, okay? Just, we're trying to get more people than biology, but we did not succeed.
How many? We've got 106. Well, we'll figure out. So you've all got to come. You've got to help me win. Ronnie can't beat me.
Oh.
Not allowed.
No. Right, goodbye. We're integrating now.
Okay, bye-bye.
Right. Now all I can see is a big TT. Can you? I don't know what's happening anymore. Can
I
you all
see you. Well, yeah, I see what you're seeing, but I'm trying to figure out how to. I can leave. Do you need me?
No.
I'll leave.
You go. Right. Okay, good. I'm back. Yes, right. Do they always give you X? Do you mean do they always give you the substitution? They do always give you the substitution in Excel, not in the new A level, but in the old A level they do. Yeah. Yeah. Okay. Right. This is how you do substitution. Okay. Ready? Ready? Okay. You go like this. Basically, now I'm done. Exactly. That's all it is. See the dx on the end? That dx on the end. Right. What I did was I got no, it's not only parametrics, it's all of substitution. Integration by parametrics is integration of parametrics is integration by substitution. Okay. Right. Watch. The dx that's on the end, you go by d theta, d theta. That's it. That's it. After that, you're just whacking stuff in. That's the only thing that you need to actually know about using substitution to integrate. That's the only thing. The only thing is that you need to do that. So you look at your integral and it will have a dx on the end or a dy or a d, whatever it is. And you literally, underneath that dx, write du or d theta or dt or whatever. And then next to it, write the d theta. So you're sort of dividing and timesing. Okay. Yeah, exactly. They sort of cancel. Yeah, exactly. So d theta, that is now more or less the end. All I need to do now is just whack stuff in. So where it says x, I'm going to write sine theta. And where it says dx by d theta, I'm going to put dx by d theta. This is the substitution that they tell you in the question. So in the question, they tell you that x is sine theta. And the integral itself had a dx on the end. You change that to dx by d theta, and then you just need to put stuff in. So here it says dx by d theta. Do you know what dx by d theta is? Cos theta. Exactly, cos theta. So here, dx by d theta, I need to know what dx by d theta is. That's not difficult. So cos theta goes there. And then x, do we know what x is? Yes, we do. It's sine theta. So sine theta goes there. And that's it. And then everything will just cancel and work itself out. And after this point, you see, this is not integration anymore. This is just mucking about with trig and mucking about. No, I don't have to. No, I don't have to. That's the whole point. I don't have to find d theta. Let me give you another one. You don't have to. It overcomplicates it. So what about this one? 2 to the x over 2 to the x, add 1 squared dx. And the substitution is u is 2 to the x. Okay? Yeah, okay, I'll do it. But yeah, no, exactly right. The mucking about is where you're going to go wrong. The mucking about is where you're going to go wrong. But you could watch me do mucking about for ages. It's not going to particularly help you because it's algebraic manipulation, and that's what you need to get super good at. Yeah. But what you can do on the course is that if you've got something where you can't work out what's gone wrong, you can take a photo of it, you can put it on as a comment, and then I can help you with it. I can help you with the specifics of mucking about. What I'm showing you here is the method. Okay. The method for integration by substitution looks like this. You get a pen. You don't need to make dx the subject. I think this is much easier. You get a pen and you go like this. By du. That's it. So you divide the dx by du and times by du. Right. That's what's going to go in there. So you differentiate Yeah, exactly. When you have limits, you just change the limits using the substitution. Exactly. The other method that people tend to use is that they try to make it say, they make this say dx equals, and it tends to go weird, and it tends to, people forget to substitute it in, and they don't really change it. So what happens is students just change the dx to a du. That's it. They just like literally, they don't do any of this. They just literally write du instead, and then it all goes horribly wrong. So I will do this one for you quickly, but I want to move on to differential equations because we've only got a quarter of an hour. Okay, so if u is 2 to the x, then that's a u, and that's a u plus 1 squared, and dx by du, well, du by dx is 2 to the x ln 2, so that would be upside down, so it would be 1 over 2 to the x ln 2, and then that's a u which cancels that, and then it's just the integral of u plus 1 to the minus 2 with 1 over ln 2 outside. I know I'm going quickly, but it's because this is just the fiddly bit, you know. I differentiated, that's how I got 2 to the x ln 2. The derivative of 2 to the x is 2 to the x ln 2. The derivative of a to the x is a to the x ln a. The derivative of 3 to the x is 3 to the x ln 3. The upside down bit is because I need dx by du, and this is du by dx, so I had to turn it upside down. Okay. I put the 1 over ln 2 outside. This 1 over ln 2, I put it outside because I always put numbers out on the outside because I'm not very good with numbers. So no, I wouldn't expand the bracket, because this is the whole point. This is the whole point. I would not expand the bracket because I know what somebody differentiated. I can see it. If somebody got u plus 1 to the minus 2, yeah, I know what they differentiated. Chain rule has been used. They must have had u plus 1 to the minus 1. That's what they must have had. So the minus came down. Yeah, there's a 1 over ln 2 there. That's just a number. The minus came down, so I'll put a minus there, and then that's it. Yeah, you could use u squared, but yeah, you could use 2 to the x minus 1. That would work. Yeah, that would work as well. Be almost the same. Why did 2x cancel out? 2 to the x, because it's u. 2 to the x is u, so that is a u and that is a u, and they cancel. Okay, but the point is the method for substitution. The method for the substitution is that you just go by du, and then you know what you've got to put there, and you know what you've got to put there, and then after that it is fiddly. You can leave the answer in terms of u if you've got limits, because then you're putting limits in. If you haven't got limits, then at the end you're quite right, you change it back to 2 to the x. I integrated that by not integrating it, by writing down what got differentiated. I didn't integrate. I never integrate. There's no such thing as integration. Yeah, 1 over ln 2 is just a number, isn't it? Like 4. It was ln 2. Ln 2 is like 4, 7, 1, 5. Because, see that if I differentiate this, see that minus? The minus would come down and then change to a minus 2. So it's not quite right. If I don't put that minus on, it's not quite right. Because if I differentiate this, I wouldn't get that, I'd get negative that. So if I put a minus there, what I mean is there's no such thing as integration, is as a verb to integrate as an active process. Because what am I doing every time I integrate? I'm just telling you what was differentiated. I'm looking at it as a puzzle. So I'm looking at the puzzle and I'm thinking, all right, so you differentiated something, examiner, and I want to know what it was that you differentiated. That's the puzzle. Yeah, fun puzzle. Yeah, okay. No, 1 over ln 2 is a number. It's like the number 4 or the number 3 or the number 2 or something. It's just sitting at the front. Numbers just sit there, they don't. Yeah, they would tell you the limits if you had to integrate. Yeah, right. We have got 10 minutes. Yeah, I think you should. You're right. You should put 2 to the x back in. Yeah. No, 4 does not integrate to 4. For a start, there's no such thing as integration. So nothing integrates to. What it is it got what got differentiated. Now, 4 on its own, what was differentiated was 4x. You're completely right. But if I have 4 lots of something, like 4 sine x, okay, what got differentiated? If I have 4 sine x, what got differentiated? Yeah, the 4 is just sitting at the front, right? So if I have 4 sine x, what got differentiated was minus 4 cos x. The 4 is just at the front. It's just 2 to the x ln 2. I think you just don't know that derivative. The derivative of a to the x, any number to the power of x, differentiated, is that number to the power of x multiplied by ln of a. That is a fact. Okay. Right, ready for some differential equations, my favourite thing in the whole world. Yes. Right, let's just do a little summary of where we are with this, okay? Right, number 1, there is no such thing as integration. There's no such thing. You look at the thing and you work out what somebody differentiated. Okay, right. Next, if you have a fraction and it isn't ln, if it's not that, then there are 3 options. Either it's actually easy, like for example, u plus 1 over root u, and you're overcomplicating it, or it's bottom heavy, in which case you use partial fractions, or it's top heavy, in which case you use algebraic division. Okay, that's if you've got a fraction that isn't just this. If you've got trig that isn't just one of the things that got differentiated, like sectan or sine or cos or something like that, if you've got trig, then it's almost certainly one of these 4. And you are supposed to just know how to deal with those. So you just change them in the way that you've memorized how to change them. So instead of sine squared, you write a half 1 minus cos, and then you double the angle. Instead of cos squared, a half 1 plus cos. Instead of tan squared, sec squared minus 1. Instead of cot squared, cosec squared minus 1. It's hard to write down there, sorry, it's a bit messy. Okay. The only other possibility for integration is parts or substitution. Substitution, they're going to tell you the substitution. And if you have substitution, then the method is as follows. You take a pen, you write by du du. That is it. Then you sub in what dx by du is, and you sub in what's going on there, and then it will become one of these immediately. Okay. For parts, you're writing down what u is and what dv by dx is. That's what they're asking you to integrate, but you're actually going to integrate this different diagonal here. You're going to integrate that diagonal. This is v, this is du by dx, and that's what you're going to integrate. If you don't know what u is, then you think LATE. Logs are u. If there aren't any logs, algebra is u. If there isn't any algebra, trig, do you get the parts formula? I'm not sure. Do you get the parts formula? I don't think so. Just look in the formula book. Google formula book for your board and see if you get it. Okay. Right. That is all of integration. What got differentiated? Fiddling around with fractions and trig, and then parts and substitution. That's the end. So the only other thing that we have to do is look at this in context, which is my favorite thing in the whole world. I've got a brilliant book about differential equations. That's easy, you just expand. Right, so that's a differential equation. I've got a really good book on differential equations, which I'm like halfway through reading. It's just loads of differential equations and then different like types of differential equation, and then loads and loads of ways of doing the differential equation. I love it. I love it. Haven't read it for a while, actually. I might read it again, and then I just sit and do all the differential equations. I think it's called differential equations. Yeah, I think differential equations, I think. Anyway, right. They're my favorite thing. So has anyone got a differential equation they'd like me to do? Like dy by dx equals dx by dy equals. So something with a dx, dy, dt, something. Can you type it in? Yeah, but I don't know what that is. Jean, like, can you say what it is? Why don't you just like type it? Dx by dy, dy by dx. We just need something with, like, and then some stuff here and some stuff here. Yeah, I'd love to do second order differential equations, Nathaniel. I'd love to. I love them. dv by dt is that, oh, this one's nice. Okay, right. dv by dt, oops, carried away with d's there. dv by dt is 30 minus 2 over 15v. Like that? Okay, right, ready? 1 times both sides by dt. That's number 1. You times both sides by dt. Number 2, you look at each side, and then if anything's on the wrong side, we're going to divide. And the wrong side is by the d. So this will be the dv side. So we're only allowed v's here, no t's allowed. Right, so now, change of variable. No, I'm just doing, so it's called separation of variables. Separation of variables. Right, so just 1 times both sides by dt. 2, look at each side and see if anything's on the wrong side. This whole thing is on the wrong side, not just the v. This whole thing, because I can't just divide both sides by v. If I divide both sides by v, then I will still have a v on this side. So I need to go 1 over 30 minus 2 over 15v. And the reason I did that is because it was on the wrong side. So at this stage, what I'm doing is looking, that's an I, looking at each side, because you can't, no, it has to be dividing and times, because what you need is thing times dv, thing times dt. You can't add and subtract, you have to multiply and divide. You have to. Because you have to divide. At this stage here, you are going to divide things that are on the wrong side. You can't add. If you add, you will get dx plus 4. And then what happens when you integrate? It doesn't even make sense. No, you can't leave the 30 because you're dividing. You must not add. You must not add, you must divide. So how would I divide and get this to move over that side but leave the 30 there? I can't, it's not possible. Not with dividing. You're only allowed dividing at this point. Okay? Oh, that's an I. That was my symbol for looking. Like, okay, so first you times both sides by dt, then you look at both sides and you divide. Divide. Okay, right, now let's look again. Are there any v's here? No. Are there any t's here? No. Good. Everything is on the correct side, so we can whack integrals on and we're ready to go. So times both sides by dt, look at both sides and divide if anything's on the wrong side. Once everything's on the right side, you can whack the integral signs on. Right, now we are back to where we started it an hour and a half ago. An hour and a half ago, we were looking at things and saying what got differentiated. So, yeah, what got differentiated? Okay, so what got differentiated there? Exactly, 2. T is what I meant when I said 2. Right, what got differentiated there? Boom, learn, exactly, done. We have sorted all of integration. Do I need anything at the front? Yes, I do, because if I differentiate this, yes, I would get 1 over, brilliant, but then I'd have to multiply by minus 2 over 15, and I don't want to. So I'm going to put 2 over 15 upside down with a minus sign at the front, and then it'll be done. Minus 15 over 2, so that will cancel. And then blah, blah, blah after that point, blah, blah, blah. This is not because of the chain rule, because I'm not integrating, don't forget, I'm writing down what got differentiated, right? What got differentiated was learn, but when you use the chain rule, you would multiply by this number, and I don't want that there, so I've put its reciprocal here so that they cancel each other out. I didn't integrate just dt, I integrated the number 1, and I said what got differentiated to get the number 1 must have been a t. Right, let's try another one. So the first thing you're going to do is multiply both sides by the dt or the dx or whatever it is on the bottom. X dy by dx equals 1 over cos y. Okay, let's see how far you can get with this. 1, multiply both sides by dx. That is the first job, always. Multiply both sides by dx. And then you just look at it. On the right-hand side, there shouldn't be any y's. So if there are, you have to divide both sides or multiply, but no adding, no subtracting. Multiply and divide. You can put the plus c wherever you like. It's traditional to put it on the right, but you can put it on the left if you want. Just don't put it on both sides, otherwise they cancel. Good. So we times both sides. It's always the same steps, always the same steps. So it's nice because you don't have to think, what am I going to do now? You times both sides by dx. Then you look at this side and you see if anything's on the wrong side. Yes, it is. So we're going to multiply both sides by cos y, because he was on the wrong side. Right, now he's on the wrong side, this guy, because it's meant to be y's on this side, so he's on the wrong side. So he should be here. Using dividing and timesing, not using adding and subtracting. Right, is everyone on the right side now? Good, so we can whack our integrals on. Good, so what got differentiated? Yay! What got differentiated? Yay! Done. Finished. Okay, it's not hard, is it? It's not hard. Everything we do gets us back to that beginning bit. And the beginning bit was where we were just like working out what got differentiated. So when we do parts, we move ourselves from this situation, which we don't want to be in, to this situation, which we can handle because we know what got differentiated. And when we have substitution, you have your dx, you change it to dx by du, you whack the dx by du in, tidy it all up, and you'll be back to where we were an hour and a half ago. Okay? If you have differential equations, you just follow these steps. Times both sides by dx, have a look, multiply, divide if anything's on the wrong side, whack the integral signs on, then you're back to the beginning. If you have fractions, it's only going to be parts or algebraic division, or you're missing the point because it's already got the derivative on the top, so it's just learn. The end solution of that one is that. Doesn't matter, does it? Plus, you can put the number on either side. It's totally up to you. Totally up to you. You can't. Do you mean connected rates of change? Yeah, it's the same as in the first year. If they get you to integrate and don't tell you any information, then you put plus C. If they give you some information, then you sub it in there, and then you can find out what C is. Exactly the same. Technically, yes, you are right. You should put moduluses around the x because you can't do ln of a negative, but you're not going to lose any marks if you don't. dy by dx. Oh, look, see, I could just do this all day. I think I'm just going to do this until Rich kicks me out. Right, dy by dx is x y plus 1. Right, I'm going to times both sides by dx. Have a look at both sides. He's on the wrong side. Now no one's on the wrong side. Now I can integrate. And by integrate, I mean write down what was differentiated. Done. Yeah, because cos differentiated is negative, sine differentiated is positive. X to the 7 minus 1 over log x. You're not going to get that. There's no way you got that from an A-level paper. Why don't I put a plus c next to ln? Here, because if we did a plus c both sides, I haven't actually put a plus c, have I? They would cancel. If I put a plus d here, then I could just move that d to the other side and then it would be an e. So yeah, I mean, it's traditional to put it on the right-hand side, but you don't have to. Just put it one side or the other, as long as you actually put it. You can put C1 and C2, but then why not add them up and make C3, which is just C? Yeah? Right, d theta by dt, d theta by dt, where has it gone? Equals 3 minus theta over 125. Right, what am I going to do first? Ln x, log x, you use parts. You think of it as 1 times log x. Yeah, times by dt. Right, he's on the wrong side. So he goes over there. Now no one's on the wrong side. Now I can integrate. And when I say integrate, I don't mean integrate because there's no such thing. I mean write down what got differentiated. Because let's think, what happens if I differentiate ln 3 minus theta? I get 1 over 3 minus theta, but then I'd have to multiply by minus 1 because of the chain rule. And also this 125 wouldn't be there. So I need 125, and I also need a minus to cancel with that minus. So I'm working out what got differentiated. And then I'm kind of, yeah, you could leave the 125 over here. Yeah, you could have 1 over 125 here and just divide by that, in which case this would just look like this. And then this would be, yeah. So long as at this stage here, when you're seeing from there to there, you're just dividing and timesing, you're not adding and subtracting. Yes. Okay, I'm going to do one more, but those of you doing biology, maybe you should go chill for a bit because otherwise your brains are going to explode. So 1 plus 2x squared dy by dx, where's it gone? X over sine squared y. Okay, so 1 plus 2x all squared dy is x over sine squared y dx. He's on the wrong side, he's on the wrong side. Sine squared y dy is equal to x over 1 plus 2x all squared dx. Everybody's on the right side. This gets changed to this. The derivative of the bottom is on the top. For squared for a quarter. I did that a little bit fast. dx by dt is k m minus x times both sides by dt. Dx is k m minus x dt. Divide both sides by m minus x. So 1 over m minus x dx is k dt. That. I changed sine squared to 1 minus cos 2y. That's double angle formula. No worries. Double angle formula from there to there. And then I wrote down what got differentiated. Good. I'm really glad it was helpful. I'm really glad. It's such an important topic, this. So, so, so important. It's like 40% of your C4. No, doesn't matter about the brackets. Good. I'm really pleased because I know that people find it really difficult and it is very hard in an hour and a half to kind of like whiz through and actually make it helpful without making you feel worse. Do you know what I mean? Because if I go too fast, then you're going to feel worse. How did I integrate 2 to the 2x? I didn't. Binomial expansion, yes, that's fine. You can use my brilliant binomial expansion method. By the way, who has seen my binomial expansion method for C4? It's so good. It's so good. It's so easy. I made it free because I wanted everyone to see it. It's on the free trial. Second to last line. Here. Do you mean going from here to here or here to here? Okay, so going from here to here is the double angle formula. Sine squared y is the same as a half 1 minus cos 2y. That's the double angle formula. That's how you integrate sine squared. Going from here to here, I wrote down what got differentiated. So what that half is that half, which is come from the double angle formula for sine. So it's here, that half is there. Why is that half there? Chain rule. That half is there because of the chain rule, because if I didn't write that half, then I wouldn't be right that that's what got differentiated. So sine 2y, if I differentiate it, I get cos 2y, but I'd have to multiply by 2, and there's no 2 there. So I need this half here because of the chain rule. This side, why is it learn? Because, do you remember what we did at the beginning? If you see a fraction, you think, what's the derivative of the bottom? So if we expand that out, it would be x over 1 plus 4x plus 4x squared. Yeah, and what happens if oh, good point. If I differentiate the bottom, I don't get that. Right, how would I do that then? No, I would do that. No, this is how I think about it. It's fine. It's all fine. I would think about it like, no, I wouldn't. No. Wait. The derivative of the bottom is 2. I know what I'd do. I'd do a sneaky thing. Hang on, let me show you what I do. Okay. So it's this thing here, right? This is actually quite a difficult one. X over 1 plus 2x all squared. Right, the bottom, I'm just going to expand it out, is 1 plus 4x squared. Do you agree that's what we're doing? Right, I wanted on the top, I wanted the derivative of the bottom. So the derivative of the bottom would be 8x plus 4, right? And I don't have 8x plus 4. Yeah, so what I could do is I could do that. Now I've got 8x, but I haven't got 4. But you know what you can do that's really good in maths? You know I want a 4 there. This is kind of sneaky. What 4? 4 hasn't gone. What I'm trying to do is make the derivative of the bottom appear on the top. This is how I'm going to get my 4. Yeah, exactly. Stick it in, they'll never know exactly. But to be fair, we now have to go like this. That's true, isn't it? I've added 4 and took 4 back off. Nah, it's not. Watch, watch, watch. Yeah, I did it. To be fair, to be fair, let me do that more slowly, and then that'll be it for today. Okay, let me do it more slowly. That is a really hard one, and I did do a trick, but it is quite a good little trick. It is a good trick. So we had x over 1 plus 2x squared. Okay. No, I think this is too sneaky sneaks. It's the sort of thing I would give to my students because I push them, but no, I don't think so. So this is what I did, right? On the bottom, if you differentiate the bottom, yeah, I will have to go in a minute because Rich will need to log in, okay? So if you differentiate the bottom, you get 2 of those times the derivative of the inside, which is 2. So you get 4, 1 plus 2x to the power of 1, which is 4 plus 8x. Okay, now what I wanted was to see that on the top. That's what I wanted. But obviously I can't see it on the top. But the thing that's lovely about maths is that often when you don't have what you want, you just have what you want. You just like have it. So if you want something, you just take it. So I want 8x. So I write 8x. Now, obviously, you do have to compensate, okay? So I can't just have 8. I have to write an 8th, but I have now got my 8 there. And now I want 4. So I'm going to have 4. Yeah, exactly. If you want it, just have it. Exactly. So I'm going to have 4, but also, obviously, I have to do this because otherwise that's not actually true. So you can't just have 4. You have to add 4 minus 4, but you can. Now I've got my 4, haven't I? I've got the 4. The 4 is there. So what that means is, and I need to be a little bit quick now, so we need to finish. So it is 1/8. 8x plus 4, that's what I wanted. Good, I've got what I wanted. Minus, and then this 4. Like that. Now that one has come from learn. That's just learn. You could use a substitution, but I don't really like using substitution. Okay, I'm going to log off. But yeah, that was a really, really hard one. I think that was like proper sneaky. That's not like your standard thing, okay? Okay, I'm going to end because it's 1:45 and you need a break and we haven't got time for question and answer. But if you get my course, which is totally worth 60 quid, then you can just post as many questions as you like and I'm all yours. I have nothing else to do other than help you for 4 weeks. I'm so glad. We're going to do Who Won the Course on Sunday. It's going to be me and Rich and Richard on Sunday answering all your questions, on a Saturday as well. And yeah, I really hope to see you and hope to work with you over the next few weeks. I've got the webinars coming up and the course is available and I keep just chucking stuff on. Good. I'm so glad. I'm really, honestly, really, really glad that it's helping you because I know I can help students in a classroom. I've been doing that for a million years, but to help students online, it's a slightly different thing. And I'm really pleased if it's actually helping you and it's working, okay? C2 we'll talk about in the webinar next Monday. Okay, see you later.